Good morning, ladies and gentlemen. Welcome to our third webinar in the Don't Fear the Fire webinar series from Finesta. Here we are here in Lahti in Finland. And this is my colleague, Ari Hokkanen, and myself. I'm Trevor Fielding, the Technical Business Manager here at Finesta. The topic of today's webinar is Transport New Energy. We'll be discussing about our fire protection coatings and thermal protection coatings for uses in battery casings and, for example, hydrogen cylinders. A little bit about the question and answer chat system that we're using here in the Teams event. So if you would like to ask a question, then please use this facility in the top right-hand corner of your screen. Just write it in the chat for questions, and we will cover these at the end of the webinar. So what are we going to talk about? So today we're going to introduce our red technology to you. This is coatings that can be applied onto composite materials to give a fire and thermal performance and protection. And more specifically, we're going to be talking about how these coatings can be used in transport new energy applications. Hydrogen cylinders and battery casings are the two main topics that we'll be covering today. Both key topics, as you're aware, in the changes that are taking place within the transportation sector to address the emissions challenge. And of course, we will be talking about how we can help achieve your goals in terms of projects relating to these applications. A little bit about ourselves. So Ari founded the company about 15 years ago and is our Chief Technology Officer here at Finesta with over 30 years of composite experience. Myself, I've been in the coatings industry since leaving university, and I'm the Technical Business Manager here at Finesta. So a little bit about the webinar itself. We're going to go through a little bit on our company and our capabilities. Then Ari will take over and introduce our red technology to you. Talk about fire testing and standards, and then the core of our presentation is going to be about the red for the new energy applications. Obviously, this is not just the only business sector, the only market that we are offering this technology to. There are plenty of additional applications where we are introducing the red coating technology, and we'll round up with a little bit about our viability assessment and what we can do for you to achieve your goals. So moving into our company and capabilities. As I mentioned, we started almost 15 years ago here in Lahti in Finland, about an hour north of Helsinki. We're an SME, we're a small company with good investment backing, and of course ISO 9001 and 14001 certified. What do we do? Specifically, we're designing, manufacturing and supplying these red coatings. These are fire and thermal protection coatings used primarily for composite and thermoplastic protection. And we're using two base technologies. One is an innovative ceramification technology, and the second is a controlled intumescent. So one's innovative, the other is using intumescent technology, but in a controlled manner. We provide material support. So in terms of our capabilities, we provide the support in terms of composite manufacturer, in terms of use of coatings with composites and thermoplastics, and also we're supplying support in terms of the burning behavior of plastics. So our understanding of how different types of thermosets and thermoplastics will respond to different fire testing protocols. In terms of coatings, we obviously want you to use our coatings in the right manner, so we provide extensive support to ensure that they're applied correctly, also that they match the color that you require, and in terms of ensuring if there's any troubleshooting or any problems, we can solve those issues very easily. A key feature of Finesta coatings and a key investment at the beginning of this year was our new fire testing lab, which pride of place is our cone calorimeter. It's a key equipment used for fire testing in our industry. And so that really completes the expertise of having the combination of fire coatings and composites all under one roof, all in the house, as it were. And there we are using different types of equipment to study both the reaction and the resistance to fire. And last but not least, of course, we're producing coatings, and we are producing coatings in our own factory. It's not toll manufactured. This is a 100% owned factory here in Lahti. We're matching those products and also developing specific products for export markets. And we have a full capability from just a small few kilos up to multi-ton orders. And of course, we want to again reiterate with ISO 9001 and 14001 compliance. Okay, that's enough from me for now. I'll pass over to Ari to introduce our red coatings technology.
Thank you, Trevor. Let's see what we have. So all the coatings, fire protection coatings, go under the trade name of red. So the red is the fire protection technology. It has nothing to do with the color of the coating. It's just refers to fire. We have different products and trade names under sub-trade names under red. We have a hybrid red, pure red, terra red, and neural red. This is more or less the topic of today. Why so many? Well, we have to have solutions for different substrates and different processes. There's no one size fits all product, and that's why we have this portfolio, and we will show them a bit later how they work. But in principle, they work all the same. As this next video shows, this is we used to have this kind of studio video, but we would like to now present this quick and dirty video because this is how you will test it anyway. So red is in this case it's a two-layer coating. So there's a underneath the intumescent coating, and on top you have a ceramification coating. So that when the heat is introduced to the surface, it will start to burn, and that's fine. The organics are going to burn away, but at the same time, the heat will transfer to underlaying coating, and that starts to expand. So we have a double reaction. We have ceramification reaction. So the top layer will turn to ceramic material, and underlay primer coating will start to expand. And this can continue for well, let's say this starts on 270 degrees, and it can continue up to 1100 degrees. And in this video, you can still see how I hope you can see the video. If not, you can see that in later when we distribute the material. But you can see that you can still keep burning it, and it's just burning stone, well, ceramic material. And if you look from the different angle, you can actually see the expansion, how much the expansion has happened, and the ceramic shield has protecting the expansion. Without the ceramic shield on top, the expansion would just be uncontrolled, but in this case, it's controlled and keeps more or less stable. It is in stable manner. And when you remove the flame, as you see, the flame is not spreading, it's just holding. And when you remove the flame, it immediately extinguishes and leaves the hard ceramic shield, protective shield on top. So what are the benefits of using red coatings? Well, in any coatings, but also in red coatings, you can repair poor and uneven surfaces. So if you demold something and there's some defects, you can easily patch them up and repair and finish it with the red. Also, you have a full production flexibility, meaning that you can paint 1 or you paint 100 or whatever you want. If you have a standard composite or standard case, you need 10 pieces. In fire retardant case, you need like 3 pieces. You can do the 3 FR and 7 knot. And of course, you can maintain and extend the life of the composite. This is also the sustainability aspect, so you can extend the life of the current part. And also, you can get all the properties in one. You can have a choice of colors and surface effects. You can have a gloss level. You can have textures. You can have red, blue, yellow, whatever. And you can have outdoor weathering, UV resistance, and hard, scratch-resistant, easy to clean surfaces. These are also decorative coating. And moreover, maybe the key point here is that it will give you the confident, consistent fire and thermal protection, because these are not incombustible coatings, these are fire protection coatings. So they protect the substrate from fire, they keep the heat out of the substrate. So you get very confident and consistent results, as we see here in the next slide. where we have measured the heat release from the standard glass fiber polyamide substrate, and without any coatings, you can see that the heat release is 152, but when you add a coating to that, you can halve that, and you can have the different same results with the 3 different samples, very consistent results. Let's go further deep into the fire testing and standards, and this is Trevor's area.
Thank you, Avi. So just wanted to go back a little bit to understanding fire in more fundamental terms, and we like to look at it in these ways. There's different parameters relating to fire, but the core parameter is really heat release. What happens when something starts to burn? Does it fuel the fire? Does it increase the burning capability and capacity, or does it tend to reduce the amount of heat that is coming out of the surface? Beyond heat release, obviously you want to see how the reaction to fire takes place. You want to see whether the fire takes hold in the first place, so how long it takes to ignite a sample, whether it's a composite or any type of material. And of course, once that sample has ignited, how quickly does the flame spread across the surface? A very important point that people tend to forget is how important to assess the spread of flame across the surface. Then we also look at the resistance to fire. So this is more what happens over a period of time to your material once you've got a fire in place, how long it takes before a structure will fail, whether there's some disintegration, some dropping, burning droplets coming from the material. And finally, the emissions. So finally, when you're looking at what's coming out of the fire, certainly for indoor applications, of course, smoke and toxicity are a key area to study, particularly in public spaces such as public transportation. And when you look at this understanding fire situation, you realize that there's a number of different regulations that can be applied according to the different sectors, but they all measure one or more of these different attributes in different ways. So there's a whole host of standards, and this can lead us to be quite confused about fire. So trying to simplify it a little bit, these are the main standards with the different transport sectors. And for example, in the marine industry, you have something called the FTP code by the International Maritime Organization that was set up. And this has different parts to it. And within our industry, for the composites world, we have several different parts that will measure different areas, if you like, of our hexagon flower of fire. If you're looking more in the rail industry, then you have, again, 3 different standards involved, and those again measuring specific parts to the contribution to fire. So there's not a single standard, it's always a compilation of 1, 2, 3, or even more standards to cover the basis to understand how materials react to fire. Question really is on this particular topic, what about new energy? What happens in the world of transportation and new energy, and particularly battery casings and hydrogen cylinders? So we have our hexagon flower, but unfortunately there isn't anything that's really established at the moment. There's no European-wide or globally regulated fire standards specific to the use of composites for pressure vessels for hydrogen use, or for composites in battery casings, for example, for automotive or rail use. So if you like, the technology is advanced before the standards have had a chance to catch up. And different companies are applying different rules and different regulations and different test protocols and different standards to this industry. Just exploring this a little bit further. So there are current standards, the EU 34, number 134, for example, for pressure cylinders, really developed for compressed natural gas and not really closely relevant enough for the use on hydrogen cylinders. Those are 2 very different gases, of course, and 2 very different materials in terms of protection. In battery casings, we have both European regulations and also the latest from China from last year in terms of standards, but they're still insufficient. They're just covering part of the requirements for the market. It's not really making sure that everything is being covered in terms of fire and thermal protection. And what's really important here is, yes, obviously, if you're talking about automotive, you're talking about personal vehicles, how long will passengers have to exit the vehicle? Or if it's a train and you're talking about members of the public, and also how long will the structure withstand the temperatures? So what is the key important requirement for these types of applications? And looking back again at our, I have forgotten one extra slide we have in here is the, yes, just a summary of those two battery casing fire standards. So we have the European standard with the burning fuel and sliding across the actual device above it. And then we have the summary of the Chinese standard, really can be contained within Annex C, which is that the battery system does not catch fire or explode under thermal runaway conditions, what we call thermal runaway, when the battery is out of control. So yes, which is the most important aspect? So returning to our hexagon flower, if we look at what important aspects here, really, when you're talking about battery casings and hydrogen cylinders, we're less interested in combustion products or burning droplets. We're far more interested perhaps in heat release. It's still whether it's going to fuel the fire or suppress the fire, how long it takes to react or how long it takes to spread the flame across a battery casing, for example. But really, the key, most important aspect of this hexagon flower really is the resistance to fire and specifically structural failure. How long will the battery casing last? How long will the hydrogen cylinder continue to perform its function of preventing the hydrogen gas from escaping or from exploding? And this leads us to thermal insulation testing. Really, we're looking at what happens in the event, in the fire event or a thermal event, and how long the structure is going to resist the temperatures that can be experienced by the cylinder or the battery casing. For example, in battery casings, but also applying to hydrogen cylinders, there's a big question about how we can develop a real meaningful test. And it's not just talking about how the temperatures and times are needed, but it's also what happens when you have this thermal explosion, this runaway of the battery disintegrates and basically explodes into particles, so also damaging the inside surface of the casing. We've got a combination of physical damage and also very high temperatures, well over 1,000 centigrade. And there's some projects underway, including the project at AZL in Aachen to develop these test protocols and to come to some general agreement within the industry on what is needed to be done. How do we prove that the casing is fit for use? Okay, I think that's enough for testing and standards for now, and I'll pass back to Ari now to introduce the specifics of the use of our technology for hydrogen cylinders.
Yeah, thanks again, Trevor. So thermal insulation tests, this is what we do here in-house to test and demonstrate our red coatings performance on a composite substrate. We use gas-fired Bunsen burner. It's a very simple but very rough and tough test. We use the blue flame 1100 max temperature, just a notch away from the composite substrate, and we measure the temperatures, ER on exposed and unexposed surfaces, but also we use thermocouples inside the composite to really see the composite structural temperature in different depths from the substrate, well, from the interface between the coating and the substrate. And we can use data and visual output to demonstrate how it works. So the temperature is recorded every minute. We use half an hour burns. Of course, there's graphs and curves to summarize results. You can see the exposed and unexposed surface temperatures, and also the inside, the composite core, how the temperature rises. And of course, panels after burning will tell you a lot about the behavior. So there will be discoloration, there will be maybe fibers exposed, and then of course there's a structural damage after the fire. When we go to the hydrogen cylinders, the red products will protect the type 4 hydrogen cylinders. How does it do that? So it will boost the thermal insulation, so it will keep the heat out from the composite itself. It will delay the structural damage because, well, there's no heat associated with the composite, and also it's a heat control. So of course some heat will be transferred, but it's in a controlled manner. And the coating delivery format is important because there will be different processes, different kind of methods to make and coat and apply. So you can, these coatings you can integrate in your filament winding process, or there are other possibilities, for example, a film, which is the new stuff that we introduced today. So introducing neon red films, because sometimes investments in liquid coating applications might be a big thing. Maybe you don't want to do that. Maybe the cycle times are too long, and instead of using liquid coatings, you can use solid coatings, which is in the form of the film. So this neon red film is designed for pressure vessels and designed for especially on the filament winding. It's a thermosetting pre-preg film, which is stable at room temperature, meaning that it's not the tacky. You don't have to freeze it. It's like a film, and you can apply it on your during your filament winding process. You can apply it as last surface on your filament wound piece, and you will need two different products. You will need that thermal insulation film, and then you will need the ceramification film. So under here you can see the black film here. That's the thermal insulation film, and the gray on top will be the ceramifying film. So all these together will give you that protection. And when you apply this on your filament wound epoxy piece, it will cross-link itself, and it will cross-link with the epoxy during the post-cure process. But also for the battery cases and their processes, we have the film. A second variation of film is the hot melt thermoplastic film. This gives the similar performance, but it will be thermoplastic, so it will be more recyclable and more fit to that sustainability aspect. There are various options to incorporate to that process. There's no, like I said, one size doesn't fit all. Next slide, we will see how neon film works on the hydrogen cylinders. So on the left side, you can see the similar kind of quick and dirty video. So the expansion here is very strong, and there is a burn, but it will go away in a 10-second mark. And on the right side, you can see before and after. So before on the left side, of course, and the right side, you can see that kind of spider web figure coming out after the burn. So this is 30-minute burn, and well, the video started to get boring because nothing really happens after the stabilization, after the ceramification, after the expansion. It's pretty boring to watch. We are not going to watch half an hour of that. We just skip to the end. So the next slide shows you how much the expansion really happens in the surface. So it's a really nice expansion and very nice thermal protection from the substrate itself. So if you look at the composite after burn, so you can see there's a hard shell, ceramic shell, and then you really have to dig into that, which we will see in a minute. So when you dig into that, you can see how much thermal isolation is found underneath, and that will give you that real protection from the substrate. And without the ceramic shield on top, there would be just a drilling effect, that the expansion will just continue and continue, and then the flame, the Bunsen burner, will just drill through that foamy substrate and go to the real composite substrate. But now it cannot penetrate the substrate because there's a ceramic shield preventing that. This video, so we can maybe skip a bit. It's not a half an hour. It's something else. But can see where we are. No, I cannot do that. But let's see. Anyway, in a couple of seconds, we can see the substrate itself. How much is exposed, how much is damaged after the burn, and yeah, it's a very delicate work with special tool, very special tools. So now you can see, when we zoom in, you can see how much the fibers are damaged, and this is the carbon fiber on top. So there was no glass fiber protective layer on. This is just a carbon fiber. And maybe the next slide will show more precise picture. So this is the afterburn. You can really see there's no too much damage on the original substrate after half an hour. If you put that in a curve, the maximum temperature was about 250 on a 3 millimeter depth from the exposed side. So between the coating and between the composite, 3 millimeters to the composite, and from the between the coating and the composite, 7 millimeters to the composite, there's a 40 degrees difference in temperatures, but it's stable more or less after 10 minutes. It stabilizes itself. Outside temperature was around 900, more or less. Then example 2, like I said, we have different products. So these are the liquid coatings with this for the different application. If you want to spray, if you want to crush, you can use 2 coatings, which are liquid ones, giving you the similar performance. And then we have let's say next generation liquid coatings, which will give you the similar performance with less thickness. The previous one was 2.6 kilograms per square meter, and the next one is 1500 grams per square meter, which is exactly the same kind of performance as the thicker one. And this was done on PMMA helium substrate. This is a thermoplastic. In conclusion, in 1500 grams per square meter, red will provide you fire and thermal protection at least for 40 minutes. We have burned 1 hour also, not too much difference. It's just consume too much gas burning it. And it's a pre-preg film or liquid coating, so you can really choose according to your process. It will anyway adhere very well to the epoxy and PMMA surfaces. Also, polyamide will work nicely. It will block over 700 degrees, so it will. The isolation factor is very nice, and the core will stay under 250 C, which means that they are mostly easily structurally stable. And the flat curves, the curves will flatline, and that is the same thing that you can see that it gives you the prolonged protection. And it's consistent. It doesn't care too much about the wall thickness of the composite. And now we go to battery casings, and this is something that Trevor can talk about.
Thank you, Ari. So yes, in terms of battery casings, the objectives really within this sector of the transport new energy market are to deliver the same or better fire performance as existing materials, which are primarily aluminium. Also, steel is also being used. And of course, the benefit to composites will be reducing the weight, trying to reduce the volume and space that the battery casing is going to take up within the vehicle, cost reduction through reduced processes, reduced materials, thinner materials, and of course, trying to make sure that we're technically improving. As we said earlier, the lack of standards means everyone wants to push these for longer, so higher temperatures for longer times. And aluminium at the moment has got some weaknesses. After about 300 centigrade, it will start to deteriorate and lose its strength. So there's a good opportunity here for composites to make way when they are coated with our red technology. In terms of protecting battery casings, there are 3 areas or 3 types of protection that we would be focused on in our development projects. One, as we mentioned earlier, is this thermal runaway. So when a battery does explode and take off and get out of control, and having to protect the casing and protect the material, and to prevent that from becoming a domino effect if you've got multiple batteries within a casing. There's the protection of the exterior. For example, if you have a fire outside of the casing, you want to make sure that that is under control and that doesn't damage the batteries inside, the expensive components. So preventing the flame spread and delaying the ignition is a part of this as well. And of course, there's the EMI shielding. So whether you can block out and ensure that the batteries are not interfering with the general electronics and running of the vehicle. And in that case, we're actually working with an external partner. We have some interesting technology there in conductive coatings to provide in terms of an EMI shielding technology for battery casings. A lot of unknowns, and there's a lot to play for at the moment. The race is still going, shall we say. So do we replace all the aluminium that's in existing battery casings, or are you just replacing the upper shell and keeping the aluminium lower shell, which could be needed because you obviously also need to have resistance to wear and tear from running a vehicle on the road. And it's still uncertain which is the best material and process. And we are actually playing a part in all these different areas. Deciding between thermosets and thermoplastics, between polyesters or epoxies, or glass or carbon fiber, perhaps even sandwich structures. There's some need perhaps for sandwich structures in trains or public vehicles, where obviously you need a longer period of time to allow people to exit, and which processes are going to be used. Perhaps the simplest ones, perhaps more like SMC or pultrusion, or something more complex may be needed to create the ideal battery case from composites and plastics. In terms of the thermal runaway testing we've done, so following a very similar method to the one that Ari introduced earlier, we've been running our Bunsen flame, we've been measuring temperatures on the outside of a plate and the inside of a plate. Of course, we're talking now 3 millimeters instead of 15 or 20 millimeter thick materials. Again, one of our favorites, the Elium material from Arkema, the polymethyl methacrylate glass fiber material. Very, very interesting results here, where we've got outside temperatures of 1000 centigrade for 20 minutes, and we're just over the 200 centigrade on the unexposed surface. Without the coating, then you'll see that blue line drift up towards the 1000 quite quickly, but we're blocking out over 700, 750 centigrade, just with a 1 millimeter, in this case, just a 1 millimeter thick coating. Second example, here we've been looking at different epoxy carbon fibers and showing that actually the choice of the epoxy resin has quite an influence, as you'd perhaps expect, over the performance. But the same characteristics, a very flat curve, a very uniform amount of temperatures being blocked out, no dramatic changes, no sudden breakdowns of that ceramic shield and that thermal barrier. Missing, in this case, 15 minutes at over 1000, this is 1100 centigrade with our two-coat system. Again, just 1 millimeter thick, giving a very significant reduction in the thermal properties on the inside surface compared to the outside surface. And one final example from the thermal runaway work that we've been doing in battery casings. There are some people who are using acetylene torches. So there you really are talking high temperatures and very aggressive fire parameters. And on this case, it's looking at how long it takes for that torch to actually burn through the substrate to the rear side, to the unexposed sides. And as you can see, our red coated SMC in this case actually doubled the period of time needed for that acetylene torch to get through and burn through that polyester glass fiber as material. So very good convincing evidence that our technology is contributing substantially to protecting these materials. I mentioned earlier, not just thermal runaway, but also looking at flame testing and looking at spread of flame is an important property in these materials. So here we have a picture that shows how we do that in our laboratory. We have this cone calorimeter, but we actually run it in a different configuration to normal. We run it in a vertical configuration, and we look at how quickly a flame will spread along the panel once it's ignited. And this is really important to demonstrate how the surface and will propagate a flame, and also how the technology works, and that we can self-extinguish, if you like, that flame once it's moving away from the cone calorimeter, once it's moving away from the heat source. We're getting some very convincing results to that as well. And in this case, this is using the polyamide 6 glass fiber material, the Tepex sheet material from the company Bond Laminates. So in conclusion, for our battery casings, we can demonstrate that we are providing good fire and thermal protection for both thermosets and thermoplastics. We can protect against the thermal runaway, certainly well over 1,000 centigrade, and certainly reaching 10-15 minutes without a problem. The films could be used. Films that Ari introduced earlier would also be useful in battery casings, because then that gives you different options in terms of placing those films in certain areas of the casing where the runaway is going to happen, and obviously saving cost and being more precise with the technology, optimizing the technology, and then also spreading the spread of flames and preventing that and reducing that spread of flame to self-extinguish and preventing the fire from taking hold if there's an external fire from underneath the vehicle. Okay, moving through to our last part of the webinar. So just a few more chapters to go in the presentation. So just wanted to cover a little bit on the additional applications. So beyond transport new energy, here are some commercial examples of our technology. A lot of them, well, they all actually for outdoor applications, showing a high degree of weather resistance, enabling composites to be used in different applications, including the marine environment. So the picture on the left is what's called a rotor sail, powering the new ferries and vessels with our white coating on it to protect it from the elements in the Baltic Sea and other across the Atlantic. In terms of footbridges, our technology has been used on single pieces of FRP composite bridges to protect them and to replace steel bridges, also utility poles, and also we have commercial business in tram roofs. Some other active market areas beyond transport new energy, you can see certainly the construction industry. We've not talked at all about that today. That was actually the subject of our previous webinar back in May. I'm making some good progress there in qualifying and commercializing RED for those applications. Side transport itself, the traditional composite use in rail and marine environments, and also, of course, in aerospace. And then we've got some more novel, unusual things happening as well. So our technology can be used perhaps in natural fiber and developing and providing fire protection for natural fiber composites, in graphic films as an alternative to painting for rail carriages. In additive manufacturing, 3D printing certainly is a good opportunity for developing and using our RED technology to enable those components to be used, for example, again, in rail or marine applications to meet the regulations, and also in the electronics industry. And of course, as we mentioned earlier, each of these areas, each of these sectors have their own certification, own requirements in terms of testing, performance, and certification. And we have collected a number of these, and we continue to collect these as we go along. All these are customer specific, so they're not something that we can usually share with a new customer, but we have good confidence we can meet those requirements, and we're happy to demonstrate that with your particular materials. So Ari will now finish the webinar, just covering the final chapters to our presentation.
Yeah, maybe the big question is that does RED provide a solution for your challenges and your material and your process? The short answer is that we don't know, but the long answer is that let's find it out with our viability assessment service, meaning that we need to have a two-way understanding of what is needed. So there will be, well, we can sign NDAs, of course, if required, but then we need to communicate mutually that what kind of goals needs to be set in order to reach targets. And of course, we need two-way commitment in order to really pull that through. So there will be technical specification. Well, you know, fire test, not what level of fire test is needed, what if there's UV involved, maybe a substrate is different. But also there's a process and process integration. So we are going to have this in a filament winding, or going to have this something else, and what are the curing times, cycle times? Is this current process, or are you going to upgrade or plan a new process? And of course, the business opportunity, the business case behind it. So what is the timeline? Is this a new business? Is this upgrade business? What are the volumes? But it doesn't end there. Of course, there's plenty of other parameters that we need to go through in order to really understand what is needed and if there is a, from our side, possibility to give you the solution. And then, of course, it's a success, also two-way success. So what does it mean in practice? In practice, it means let's discuss. Let's have that Teams meeting, or let's have physical meeting, and let's discuss about your technical requirements. Let's discuss about the process you would like to integrate, or how you would like to do that. Maybe it's a new process, and let's talk about business opportunity. And you can send us a sample if this is viable. Let's proceed that you will send a sample of your substrate, and we will run appropriate tests, quick and dirty small tests, and analyze the results that if that's really possible, and then we can recommend next steps. That's how we can set the goals, we can set the timelines, we can set all the requirements in a mutual manner, and then go forward. In a summary, to end the webinar is that RED will enable composites to meet their fire and thermal standards. And you don't have to change your composite or your substrate or material. You can use that material that you have today with all calculations have done, you just add RED on top. We will be a fully supporting partner for your business because we are the leading company in a fire thermal composite sector. Well, as we said, we supply specialty protective coating, and we have fire laboratory for testing and results and analysis, and that's available to you through our viability assessment service. But the tagline, maybe, I don't know if Trevor has tattooed this already in his bag, but the fire protective coatings will complete composite. If not, we will do it after the webinar. And still, we have this instruction for questions. As a reminder, I mean, there are plenty of questions, I guess.
We've got 7 questions, Ari, actually, yes.
Yeah.
So we can go to the questions. Okay, so the first question was, can coatings be applied on cylindrical surfaces, and what is the maximum temperature surface can bear without swelling?
Yes, they can be applied to cylindrical surfaces. The swelling will start at 217, but I would, if you talk about post-curing temperature, I would keep it under 200, so 150, 170 C as a post-curing temperature.
Okay. Next question we have from Sanket was near-on-red surface inside coating will be reusable after expansion surface is removed. So I think the expansion surface, that is the near-on-red. So when it expands, that is using up, if you like, that film, and the intumescent is now not functioning. That is now the result of the thermal protection.
It's disposable film after the fire event.
Yeah. The next question we have, in case of a battery casing, what is the carbon footprint impact versus aluminium? So at the moment, we haven't got as far as doing any carbon footprint work specifically to battery casings. It would be very interesting for us to start some work on that. This is still quite new technology, but we will certainly get back to you, Marco, when we have some information on carbon footprinting of our technology against existing technology.
But let's say there are no halogens inside, there's no bad stuff inside, so mostly the ceramification happens without any fire retardants. And we don't use any blacklist material.
Okay. Next question I'm going through here is, which thickness of the coating is needed as a minimum to get sufficient fire resistance, for example, for a battery case cover?
Well, at 1500 total thickness, I would say is feasible to get that kind of protection we showed. If you go lower, yes, you can go lower, but then again, it's against time and temperature.
Again, a question about how about overall sustainability, can your products be removed from the substrates or recycled in any way?
Well, the thermoplastic Neoron is recyclable as a thermoplastic it is, and it can be removed, of course, mechanically, but that's not the point. But also it can be removed with certain solvents that you can dilute in the certain solvent, so you can remove it, and the solvent is then removed from the debris. But yeah, it's a thermoplastic in the way. It's the best way to describe it.
Okay, we now have a question from Martin at Deutsche Bahn. Have you tried the railway spread of flame test with a specimen where the coating has been damaged, i.e. by scoring a line through it? This is always given as a reason by approvals bodies, by fire protection components are not favoured in rail. So it'd be good to have evidence to show what level of damage will result in a test fail.
We haven't done that.
We haven't done that.
No.
We ought to do that, I think, yes. Obviously, if coatings are damaged by people scratching them with luggage or whatever on the inside of trains, it will be interesting to see. Generally, the spread of flame, the self-extinguishing nature of the technology should work, but we should perhaps put more definition on the width of damage and the amount of damage.
Of course, you can see visually if the top coating is damaged because the underlaying coating is different color, but still performance needs to be tested.
Another question, what is the economic impact compared to commonly used solutions like mica sheets?
Well, we haven't calculated that too much.
Not been assessed.
But these are the final surface, so you don't need to. With the mica sheets, you still need to protect it from UV and keep them in color. But this is the ready decorative surface, so it's one step less to make a final product.
I think certainly if we can make the polyester SMC work for battery casings, which is a rather economically viable and challenging approach, then if that works, then I would say it should look very favourable. If we have to use something more sophisticated in terms of the composite resin and the base materials, then not so much. And also, of course, carbon fibre in terms of the hydrogen cylinders. If there is at some stage the possibility to move to perhaps non-carbon fibre hydrogen cylinders, would take a big cost away from that technology. Okay, a few more questions coming up. I can just click on them. How can your films be integrated into composite processes like wet compression molding or RTM?
Well, maybe not in a wet film process or wet RTM. I would say it's in after demolding. So you can put the film after demolding and can put it on top of the RTM or pull through the process product.
Question from Michael: do you also offer clear coatings?
We offer clear coatings. At some extent, you can have a flame spread, you can have ignitability improved. Well, less the performance improved. But for the thermal runaway and for the thermal insulation, the fully transparent system does not exist here.
One to work on.
Yes, it's on under the table.
And then final question that I have at the moment on the chat is, how about the electrical properties? Is the coating electrically conductive?
They are not electrically conductive when they are not exposed to fire, but when they are exposed to fire after the ceramification, there is some conductivity after the ceramification, but not when they are not when they are in the normal stage, not on the burnt stage.
And then we have the EMI shielding, where we would be using a conductive layer to provide the EMI shielding properties. So that would be a separate topic, a separate type of product. Okay, I think that's all the questions that have come in, Ari.
Yeah, I think we need to say thank you. I think we're right on time. We couldn't see this video through, but I will skip it.
Skip to the end.
Skip to the end. So, thank you very much for attending, and I think we need to see you next time.
Yes, and we'll share the presentation and link to the webinar for you to look at afterwards as well. Thanks very much for your interest.
Thank you.